Hi guys, so we're going to continue talking about gases and gas laws by focusing on Boyle's law and Charles' law. So the first one that we're going to look at is Boyle's law. And this one is seeing how pressure and volume affect each other when we're looking at gases. So before I even talk about it, I'm gonna do a little quick example here. So here I have a syringe. This is really what I use to cook with when I make a turkey. I will use this to inject. I have like a little needle and I use it to inject flavored oils under the skin of the turkey. Kind of gross sounding, right? But anyway, today I've taken the needle off of it and I have put a marshmallow inside there. So you can see that marshmallow in there. And I'm going to put my finger over the end here. So it is a sealed container. And I am going to press the plunger down, which means that I'm putting the marshmallow under pressure. And, oh, I let go. I got to do it again. All right, here we go. Okay, so finger over. This is hard to do. Finger over, and I'm going to put that marshmallow under pressure. And hopefully you can see that marshmallow is becoming smaller. So as pressure increases, I'm pushing really hard. That's as far as I can go. The volume of the marshmallow decreases. And as I release the pressure and I let the air back in there so that there's less pressure, the volume of the marshmallow increases. So that means that pressure and volume are inversely related. As pressure increases, volume decreased. They did the opposite of each other. So that means that our formula is going to be pressure times volume. The initial pressure times the initial volume is going to equal the final pressure and the final volume. And here we have, if we were to actually get some data measuring gas molecules as we put them under pressure. As we increase the pressure, we would see the volume decrease, and as we decrease the pressure, we would see the volume increase. Here's a little cartoon drawing of that. We have a piston, a sealed container. Here we have it with 1 atmosphere pressure and 4 liters of volume. As we increase the pressure to 2 atmospheres of pressure, so from 1 to 2, we've doubled the pressure, we are going to half the volume. So now it is 2 liters of volume. And so we can see as we increase pressure, we decrease volume. All right, and then here we have an example problem. If a balloon is filled with 25 liters of air at 1 atmosphere of pressure, if the pressure is changed to 1.5 atmospheres, so we're increasing the pressure, what is the new volume? Well, without even looking at a formula, we already learned that if we increase pressure, we decrease volume. So we expect our volume to be less than the original 25 liters that we have right there. So we identify our variables, we write them out, initial volume, initial pressure. We don't know what the final volume is, but we know what the final pressure is. We pop them into our formula there. We've got to do a little rearranging, a little algebra. When we rearrange to solve for the final volume, we move that final pressure over to the other side. So we're going to divide both sides by the final pressure, and we end up with 17 liters of volume, which is indeed less than our initial volume of 25 liters. So this is just an example problem. Please put that in your notes, and we will do some problems together off of our practice sheets. All right, let's look at Charles now. Charles' law, we're going to keep the pressure constant. In Boyle's law, we changed the pressure, but now we're going to keep it constant, and we're going to look at how temperature affects volume. So when we increase temperature, we increase volume. So they are directly related. If we heat something up, we give it more kinetic energy and it's going to expand. So a really good example of that is a balloon, right? So if we have a balloon and it's at normal room temperature and we take it outside on a really hot day, that balloon is going to expand, and it could even expand to the point of popping, right? And if we fill a balloon at normal room temperature and then we take it outside on a really cold day, it's going to deflate and droop, and it might look like it's losing air, but really that air is compressing together. It's huddling together because it's losing that kinetic energy. So when we have things that are directly related, we divide. And we can see our formula here that our initial volume divided by our initial temperature is going to equal our final volume divided by our final temperature. And here, if we were to take that balloon experiment of having a balloon in hot or cold and put it into a graph, we would see that as we increase the temperature, our volume also increases. It's directly related right there. And here we have, going back to our pistons, looking at an example, we have 1 atmosphere of pressure. We have a volume of 0.5 liters, and our temperature is 200 Kelvin. If we heat it, see how our arrow is going this way? If we heat it, so we're doubling the temperature to 400 Kelvin, pressure is still constant, we are going to double that volume. So double the temperature, double the volume. They are directly in relation to one another. And if we take that same cylinder and we cool it down to half the temperature, we're going to have half the volume. All right, we're going to finish off with an example equation here. Just put this in your notes. We will do some practice problems together. At 25 degrees Celsius, a gas is expanded from 2.5 liters to 4.1 liters. So we have the gas expanding, all right? Assuming pressure remains constant, what is the final temperature? Well, we know that these two guys are directly related. So if the volume is getting bigger, is the temperature going to go up or go down? It's going to go up. Let's take a look. So we identify our variables: initial volume, initial temperature. We've got to add 273 to get it on that Kelvin range. We have our final volume, but we do not know our final temperature. We take the formula for Charles' law. We're going to rearrange it to solve for final temperature. Little extra rearranging there. You don't need to memorize this formula. You can use your algebra to rearrange to solve for T2, and if you're not seeing how to do that, we can do that together in our synchronous class time. And so here we're filling in our information, and we solve that we get 488 Kelvin, but that's not sig figs, so we take it to 490 Kelvin, which indeed, when we look back at our original 298 Kelvin initial temperature, our temperature did increase just like the volume did. All right, so that's it for Boyles and Charles' law, and we'll do some practice problems together.